Yeah, we talked about the physical and the chemical, physical and chemical properties and change, and we can um, we can go there and then look at some of the examples we had. So let's look at some of the examples we had before. We can take another one this time. Let's see. Here we have, here, for example, it's already the answers are given to you. Okay, so this is the answer here given to you. But you can look at this worksheet with all the answers are given to you. How about one does not have an answer? This is the one we started last time. We finished all this here, this part here. Sorry, I have to. Um, we finished, I think, all of this here. Correct. So let's finish here. Milk taste is changing. It's sour. So what will be chemical or physical? Chemical or physical? Chemical, because that cannot happen by itself. It has to have through a chemical reaction. Correct? There is a bacteria there, and the bacteria is producing some chemicals that's affecting the milk. Anytime you have things changing from the material itself, there's something chemical going on. If you have a rusty iron, rusty car, that's a chemical. Iron is iron, but then the rust is moisture coming out, oxidation coming out, and this is a chemical reaction. Sugar dissolves in H2O, chemical or physical? What do you think? Physical. Solubility is always physical, correct? Now, wood rots, the same thing. Iron rusts, wood rots. What is that? Physical or chemical? What's that? That's a chemical. Anything change the material itself, it has to go through chemical reaction. Anything change the original of the material or the matter, this has to be chemical. Because if this wood will be broken in small pieces like powder, so it means you cannot return this piece of wood as is before. Correct? So physical, I can recover this material back, like sugar and H2O. I can evaporate H2O and then get it out, collect it, and then sugar will be as crystals at the bottom. So I can separate them into items. Pancakes cook. Pancake cooks. You start with the dough, correct? Flour dough, correct? And you start baking soda there, and then you have carbon dioxide to take the dough. Now, when you start cooking, you put what? Fire there, correct? Then you instigate what? Chemical reaction. Because the taste of the dough is no longer you started with. Can you take this pancake after cooking back to its original dough? Anytime I cannot go back, that's a chemical. Everybody is following? Anytime the process is irreversible, I cannot go back and reproduce my stuff, therefore it has to be chemical. So that's it. So this is chemical. Grass grows. Well, the grass grows, and then you hire somebody to cut the grass. It will come back again next year, correct? Nothing happened to the grass. So this is, this is reversible. It can come back again and again and again. So this is physical. A tire is inflated. I have a flat tire. Well, that's physical or chemical? What's that? Physical, not chemical, because you put the air inside the tire, and what will happen? The tire will be non-inflated. It will be okay. So this is physical. Food is digested. You have to watch. Food is digested. Digested where? I mean, in humans and animals, in the stomach of all the animals, correct? So what's inside the animals who digest the food? What we have inside? 2% of what? What acid? Hydrochloric acid, correct? So hydrochloric acid is reacting with that food to break it down in small pieces, correct? Now those pieces, you cannot recover them. If you open somebody's stomach and recover that food, can you recover it? No, because already digested into enzymes, into some of the hormones, whatever inside, amino acids, proteins, whatever inside that food is already broken down and chopped down to different material. Are you following me here? You cannot return to the original food you have. You have eaten a piece of meat. Well, in the meat you have a lot of amino acids, proteins. Proteins is multiple amino acids connected together. So when you let HCl reacting with it and it digests it and you get a lot of dissolved meat, now out of this meat will be amino acid coming out, some minerals coming out. So, but you cannot take stomach, open somebody's stomach and they get the piece of meat back again. Can I get the piece of meat back again? No, no. So therefore, this is what? Chemical. Anytime I can't reverse the process, that's a chemical. Paper, a towel absorbs carbon. So that's chemical or physical? Physical, because I can't take this towel here or piece of paper, put it in the sun, the H2O will evaporate, then I have the piece of towel dry, correct? Okay, so this is physical. So that's what we'll cover this point. Now we'll go to see that we have 3 types of. Here you have only 2, but we have another one. We have 3 measuring systems. We have 3 measuring systems, really 3, and those are here. We have 3 measuring systems. The one is it's not mentioned here. The one we are not using it per se for science. We are using it for commercial and for businesses, for commercial purposes. So we have the first one here, and it's really widely used, but mostly for commercial purposes. English system, measuring system. Then we have this. We have 3 measuring systems. Then we have metric. And then number 3, we have SI system. Well, SI, as I said, this is in French. Whoever speaks French, the adjective comes before the noun. That's the opposite to German language, I know, and that's the opposite to English language, I know. So we have in English and in German languages both. First, first the adjective will come. Clever. This is a very hard-working student. You get the adjective, whatever. I mean, you describe this to the noun, but here they give you the name, the noun, then they give you the whatever after that. So this is system, international system. So the opposite, if I translate it from French, this is international system. But the French is bringing the noun first, and then whatever adjective at the end. So the metric is, the English is well known for commercial purposes. For example, we have here the length, as we will do this one here in the lab today, the mass and the volume, correct? We have 3 measuring units. So we can look at the all this one here. So the metric is the easiest and the most. This is used measuring system, because then you can easy to convert from here to here, from here to here. Somebody will tell me why it's easy to convert from metric to English and vice versa, and the metric to SI system, measuring system, easy. Well, it turns out metric is always power of 10. So then it's easy when you have exponents, you don't deal with a lot of fraction, correct? The English and the SI measuring systems, they have fractions in them. That's headache, correct? Sometimes headache. You have to have a calculator. But the metric is nice. You don't have to have a lot of fractions. So you base your stuff on power, exponent, power of 10, correct? So now, for example, the metric in the length, that's a metric one. Here we are, metric system. Those called basic units. This is basic units. So in the length we use meter, small m, okay, not centimeter, we use the meter. So in the mass we use the metric gram, the basic unit, and the volume we use liter. Now if I go for the English, the length I use what? Somebody will tell me what we use for English. The length, the basic unit, will be what? I heard the correct answer, but loud. No, not inches, a little bit small, like centimeter. We use the foot. So we have to use the foot. Okay. And the mass, we use what? We said we use a gram, but the mass we use what? The pound, correct? Yes. We use the pound. And the volume, we use what? It has not to be the smallest. We use the gallon. Yeah, so you can see, as again, it's always when you go back and forth, it's problematic. But by the time when you use the system together, you can tell, correct? So those are basic unit in the metric. Those are basic unit in the English. Foot for the length, pound for the mass, and gallon for the volume. Now, how many gallons? How many liter in 1 gallon? So the gallon is big, correct? Gallon of milk. So how many liters is that? Somebody will tell me. Guessing. Can you guess? The gallon of milk, how many liters? So I'm going from English. So a gallon, that's English, correct? And then I want to see liter, that's a metric. So this is metric, and this is English, correct? So this is English. So how many? Well, it turns out very funny about this situation. You have how many types of gallons we have? Somebody will tell me? Too many, correct? Not too many, but few. We have American gallon, we have Canadian gallon, we have British gallon, we have Australian gallon. And they differ in the digits after the decimal. But all in all, in general, the American gallon is you look at this one, 3.7, and then the number after 7, that's what will have the variation, whether it's British or Canadian or Australian or American. We have 3.74, I think. You can Google it. But then there's a fraction of there after the decimal will change. Then will change the value of the definition. Are you following me here? So, well, it turns out it does not really make any sense. But if you have 18-wheeler and you fill it with how many gallons, it comes out a lot of money, correct? Those fraction of after the decimal, they add up. But for our car, just 15 gallons or so, that will not have that much of effect, correct? So, but yeah, so you will see that's the after the 7, that's the issue. Oops, that's the issue we have here after the 7, the definition. So that's a fraction. So I'm going from 1 gallon whole unit, but I have fractional value of it in the metric, 3.74, American gallon. So and so on. So then you have the SI. Well, the SI is after World War II, after 1945, after World War II was in Germany. You know the history. The scientific community came in France, and they decided to have a system that will have, because some of the countries in Europe, especially UK, United Kingdom, they are using what? They don't use the metric system. German are using the metric system. The British are using what? The English system. So they decided to come after World War II, a scientific community, and decide to have international system. That's it does not use metric, or it does not use English. So it will be unified. You will see a lot of textbook nowadays are going through this. You will see a lot of SI units are used, heavily used. So we are going out of the metric, we are going out of English. We have the unified scientific measuring system. So, but however, it's very funny about the SI is a big cheater. They are cheating themselves, the SI. They said we are borrowing. So they are borrowing mostly from the metric system. So the metric system, the basic unit of the length is what? Is meter. And the SI is what's the SI? Is meter, the same thing. Are you following me here? So they are taking a lot of stuff from the metric. And I think part of it because the conference was in France, so France is using metric system. So the mass, a little bit different. The mass, if I look at this one here, take this one here out. So the mass here, the mass is using the gram, the small unit, the gram in the metric. However, the SI uses what? Uses kilogram. And you can see the symbol of the kilogram, small k, g. Temperature. Temperature is what we are using temperature. Temperature. We don't have it in the metric. What we use metric, temperature. If I put temperature here. For metric, what we using? Centigrade Celsius. Perfect. Thank you. C, capital C. And there is a small tiny like a circle on the top. This means the circle, small tiny circle means degree, centigrade Celsius. So what we use for English? Fahrenheit, correct. Circle and capital F. And what we use for the SI unit? Kelvin, capital K. See here, the kilogram, small k. Here, look, where is it? Here it is, small k. The temperature is capital K. This is capital K. Here is small k. So small k for kilogram and capital K for Kelvin temperature, correct? The only thing, all the system, the three systems are in the same wavelength is the time. The basic unit of the metric, English, and SI is seconds. S, small s, seconds. So whether you are in metric or you are in English or you are in SI, the time has to be the same basic unit, second, correct? Amount of substance, same like time, same thing more. Whether you are in English or you are in the metric or you are in SI, they use the mole, correct? That's the same thing. Those are two items are the same. Electrical current, they are using it to SI ampere, the same thing. Though some units are really the same. Luminous intensity, lumen, those are the same. So they are not changing those units. But the main thing is temperature is totally different. And the mass and the volume and the length are different from each other. Now, at the end of the chapter, we know how to convert those. Now, when you take the quiz or the exam, it's an open book. You have to print out the table of the conversion, correct? 1 yard, how many centimeters? Somebody will tell me. Somebody who is working as a carpenter one day in your life. How many? If you see a carpenter, they have all this in their head. They don't go for, they know how to. An inch, how much is centimeter? 2.54 centimeter. Close to 3 centimeters, 2.54 centimeters. A mile, how many kilometers? Which is greater, a mile or a kilometer? That's for the length. The mile is greater by how much? How much? The mile is 1.62 kilometers. How about the grams and the pounds? The pounds and the grams. So which is greater, pound or gram? I heard gram when somebody said pound. At the pound, 1 pound, how much is a gram? So those things you don't have to memorize. If that's the final exam, that will have to be given to you, correct? But for your sake, if you have the exam, I'm not giving to you. I'm giving it's an open book. So download, I think it's in iCollege. You will see it. I put for you a table. You might not like it. You can Google one and print it out. So a pound is 454 grams, correct? A pound. So a kilo is how many? So you can look at the table, but your head is telling you the ratio between English always about ratio of 2, roughly is 2. Roughly of what? 2. So 1 kilo is almost 2 pounds almost. Okay, guys. So anyway, so look at this. I put this one here in iCollege. This conversion units tables. You don't have to memorize it. In the final exam will be given to you. But in the quizzes and exams, I'm not giving to you. I'm telling you to print out your favorite one. I put for you one. If you like it, you can use it. You can Google one and print it, because you can't Google during the exam and quiz. The lockdown browser will not let you. And if you insist, the whole quiz will be frozen. You cannot continue in that quiz. So anyway, any question you have so far? Any question? Any question? Ask. Don't hesitate. Ask. Okay, guys. So as you can see, the best measuring tool is the metric one. It's the easiest one, and that's the next. Can I take this one out? The next slide will show you why I'm saying this. Not because I prefer metric. No, they are the same. But the good thing about the metric is I'm using this slide here. See here? With this slide here is all the metric power of 10, correct? So you can see whenever I see this one here, then you can see we are not using the X, which is 1018, and we are using mostly from here. And then I'll show you how to do the conversion. Okay, so we use tera, 10 power 12. What is tera in commercial units? What we call tera? I said terabytes, tera whatever. Tera. What's tera is in commercial one? If I go to the Wall Street, I want to see what tera is. How much is it? Come on, don't let me down. You know that. So what we have? Come on, terabytes, not the bytes of the computer. Tera dollar. I said tera dollar. How much is it? That's a trillion, guys. Don't let me down. Trillion. 10 power what? 12. So how about 10 power 9. What we call that? We call this one gigabyte, correct? 10 power 9. But what's the commercial name? If I go to the Wall Street again, I have giga dollar. How much is it? A billion. Yeah, now you get it now. So it's easy. So 10 power 9 is a billion. 10 power 12 is a trillion, correct? And 10 power 6 will be what? A million. No, 1,000. That's a cheap. That's cheap. That's very cheap. No. We have not to be very cheap. No, that's a million. So 10 power 6 is a million. So 10 power 3 then is a kilo. Then we have 1,000. Are you following me here? So you have to know these powers in terms of the metric and in terms of the commercial name. We don't use teradollar. We are not using teradollar. I mean, we can terabyte, tera any noun inside, tera pencils, tera books, terabytes, tera pencils, tera books, tera screen. Tera means trillion, correct? But you have to know the commercial sense of this. Not only 10 power 12 or 10 power 9, but we have to know the commercial sense of it. So anyway, so we will see, as you can see, the good thing about this is all of it's about power. And I'll leave the conversion at the end of the chapter because you will let me repeat myself 1,000 times. There will be a lot of confusion. And I don't want to hit the confusion now. I'll hit maybe by next week when we end up this chapter with the conversion. There's a lot of confusion. You go by the zeros to the left, zero to the right. I'm showing homemade. That's my idea. It's easy to follow. You'll not get any mistake in conversion between those powers, correct? Or you want the confusion now? You want the confusion now? No? Okay, good. Just asking. We'll keep it at the end because that's confusing because a lot of students, they did not see how to convert. So if I say I have trillion bytes and I want to make a trillion bytes, I want to convert it to centibytes. So I'm going from the trillion, which is tera, 1012, to the centi here, which is 10 minus 2. So that's a lot of confusion there. The students will have a hard time to follow. But then when I repeat myself a couple of times, everybody will get. We'll come back and do some conversion here. But I just give you heads on. It's very confusing, but we'll get it. I'll repeat myself a couple of times until we get everything there. So this is the metric, which is really I'm not preferring metric or something, but it's easy to follow this power of the power exponent. It's very easy, and it has a distinct names. Actually, if the power exponent is positive, you get in general is capital letters. There's some exception. Kilo is a small k because of the fact is the capital K is reserved for Kelvin, and this hecto is small h. Deca is dA. So you will see those are exception. But in general, all the minus exponent, the negative exponent, all of them are not capital letters, small letter. You can see them here. All those are small letters. Okay, guys? So let's look at well, scientific notation is not going through that. You can, as I said, in math, remember what I told you. If you need any help, I'll show you. This is straightforward, but I can show you. If you go to the left, this is to the left. So you are shrinking the value. The value is shrinking, correct? And the exponent is positive. Exponent is positive. So 10 plus whatever the exponent is. So if you go to the right, so then you have the opposite. The value is expanding. The value is expanding. And the exponent is negative. Exponent is negative. So if I want to make the value very large, then I have to go what? To the right, the exponent will be negative. If I want to shrink the value, I have to go to the left, the exponent will be positive. Those here are the examples, but I think there is an error here in this slide. Somebody will confirm there is an error here. This is a large value, correct? I want to squeeze it. So I move the decimal. How many digits? Somebody will, how many digits, guys? 6, but I have here what? 5. 5 is wrong. It has to be -6. I went to the right. I moved the decimal here to here. 6 digits, so it will be 10 minus 6, not 5, correct? So if I go to the left, the exponent will be negative. If I go to the right, the exponent, or the whole thing will be this is, I went to there to the, yeah. So I'm just here negative, and if I go to the other side, this one here, I can make it what? It will be positive. So how many? 1, 2, 3, 4, 5. 6 to the power 5. So are you following me here? So that's, I'm not going through this, but if you need help, just let me know. I'll be willing to have a one-on-one review with all this math stuff. So any questions so far? Any questions so far? Okay, everything is good. So let's look at the next slide here. Okay, so this will be exact and measured numbers. So what's exact and measured numbers? Exact numbers, they are by definition. For example, I will say I have a definition, whatever. The density of H2O, for example, density, oops, sorry. The density of H2O is, as you will see it here, density of H2O at 25 degrees Celsius is 1 gram per 1 ml. So this is an exact value, correct? That's an exact value. Or a pound is 454 grams. Those are exact value. As soon as I put decimal inside, then I'm going from exact value to what? To measured number. The measured number, it has to have a decimal because there is uncertain trials, so it will not be exact. This is 1 gram per 1 ml. That's the density, correct? Another example of the exact, 100%. 100%, that's an exact number. But as soon as I say, well, okay, 100.03%. Well, now this is not more exact. I introduce the uncertainty here, the last number here. I'm not certain about it. So that's what the difference between exact and measured. The measured number is always you have uncertain point, which is the last digits after the decimal. That's always is open for uncertain situation. So, but if I have put no decimal, that's exact value. With the decimal, then I have introduced to myself uncertain digits, the last digit, which will be uncertain. So, this just for yourself, because that will come up to significant figures in a minute. So here it is. Now to significant figures. So I will open this one here. So significant figures is to express, is a procedure to express the uncertainty in a value. Okay, and as you can see in the lab, we will have two types of balances: the top load balance and the analytical balance, which has glasses all over the places, covered with glass, so it's closed, correct? So the uncertainty in both, they have uncertain values after the last digit of them. So the maximum for the top load, I'm not sure about the analytical, you can check it out. But the one here, the top load one, which will be looking like this, you can see it here. You see it in the lab here. And here's snap one for calibration one. So you put your stuff here on the tab and measure. So you look at the back, it will give you plus maximum. Max capacity here will tell you is, will be, 300 grams plus minus 0.5 gram. So it means this can go from 300.5 gram can go, or to 295, or correct, if you put 0.5 here, yeah, grams. So you have a half a gram uncertain value in this balance. So that's that where the error can be. So half a gram is like an error. That's uncertain, and that's what really the significant figure is always expressing, this uncertainty in a value. You will see every equipment you will be using, it has uncertain error there. So it's not control. You cannot control it as part of the inheritance. They call it inheritance error. Correct? That's what I give the students in the lab. If you have two cars, brand new, they come from the two lanes of manufacturing lanes. Are they identical? Everything? No, it can't be. Because the computer who had done the first lane is not the computer who has done the second lane. And the computer was manufactured, the first lane has an error which is not identical in the computer, the second one. Are you following me here? You cannot produce something 100%. You cannot. Because every time you use a machine, the machine you are using, it has inherited part of the manufacturing of it, is there is an error. And it can be minimum, it can be small. And you can hear every time you have recalling your car back because there is, after 1 or 2 years, they found there's an error there. Correct? You heard about that. So that's part of the inherent errors, which is sometimes very hard to detect, very hard to control, but they can then fix it after a while. So now let's look at the significant figure. I want to see a number here, and we have to determine the significant figure of it. So I have here 0, 0, 0. Here is my decimal. 0, 0, 3, 1, 4, 0, 0, 0, 3, 2, 5, 0, 0. So the question is, how many sig figs does this value have? How many significant figures? So sig figs does this value have? That's a question. Well, it turns out to be, and we can look into the whole thing here. Since we don't have a whole number or exact number, whole number or exact number or exact number is missing here, which is 1 to 9, correct? Which is 1 to 9. Those are the exact number. We don't have this number in front of this. So those zeros here are called decorating zeros, just for decoration. And the Excel files, Excel software does not like them. If you zero like this and you enter, the Excel software will take them out. Take just the decimal and the beyond the decimal, but no zeros. Does not like this. It's for decoration. Why waste the Excel file for? That's what the software is telling us. So those are not significant. Not significant. How about those zeros here? There is no exact number there missing. No exact whole number from 1 to 9. So those are locating zeros. They locate the decimal, correct? They locate the decimal. Those are not significant. Not significant, correct? This is whole number or exact number. Exact whole number or numbers. There's always significant. And with those two here, from 1 to 9, those are always significant. Now, those zeros here are called trapped zeros. They're trapped between exact whole numbers between 3 in this case and 4. Trap 0 between 3 and 4, correct? And they are always, so here it is, write it here, trapped zeros are always significant. Okay, guys, always significant. Now, zeros coming at the end here, they are significant, and so this they call it end zeros, or zeros at the end. End zeros, let's write another color here, maybe green. So the end zeros are significant if they meet two conditions at the same time. If they meet two conditions that's D here, at the same time. What are those two conditions? Well, the first one here is, I will take this, let me take this tab so I have space. So it is. So what's the two conditions? The first condition is they come after a whole exact number. So first is, the first condition here, first condition, they come it's not allowing me to write anyway, so they come here after whole exact number. The second condition is the decimal is present. Decimal is present. So are they meeting this? Yes, the decimal is present, okay? Decimal is present, and here they come after the 5, a whole exact number. So those are now significant. Those are significant. So how many now we have? Those are not significant. Those 2 zeros are not significant. The 3 are the whole number, yes. So we have at the top one, yes, the end zeros, yes, and the exact number, yes. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So how many sigfigs we have? 11 significant figures. So this, we answered the question is, how much significant figures does this value have? The answer is, this value does have 11 significant figures. Okay, guys? Now, this might be just general theoretical stuff. Let's do a real worksheet so we can look at the some of the problems we have. Everybody has it? Can I take it out? It will be in the video, so I hope. So everybody has it? Take it out? Okay, let's take this one out. And so here it is. This is the conversion factor. We'll come back to it. So, but let's do here. Okay, guys, let's do some of those here, and then I'll tell you the some stuff here. The values with the power, they are not significant. If I will tell you, just a note here, that's very important. The value here, for example, 3.40, 10 power 3. So how many significant figures we have? Well, this exponent here is not part of the exponent here, is not part of significant figures. So we have how many here? 3. Why the 0 at the end is significant? It's meeting what? 2 conditions. There is a decimal present, and it's coming after a whole exact number. Okay, guys? So this is 3 sigfigs. How about 10 power 3? It's not part of the consideration. We don't consider what the exponent. The same thing with another example, 3.40 log of 2. Well, same thing here. Log or ln or ln2, 3.4, those are not part of the sigfigs. Only those numbers with the decimal inside them or without decimal. But log, ln, power exponent, they are not part of the sigfigs. The same thing with the e function, which is the opposite, the anti-function of ln, correct? 3.0, e function of maybe minus 2, e function. So this e function is not part of, so we have still 3. Are you following me here? Are this following? So let's do those here, and yeah, the first one. How many sigfigs? Now there is a comma, and this is sometimes very confusing. There is a comma. Comma has nothing to do with the decimal. Comma show us, the comma here show us whether it's thousands or millions or I mean millions, trillions, thousands or hundreds, correct? So this one here show us that's 1278, and this one after the comma, that will tell us what? That's a thousands, correct? So this is 1278, and then you have decimal 50. So don't worry about the comma. The comma just showing us the amount of the value, whether it's thousands, hundreds, correct? Trillions, billions, whatever that really is. But anyway, so how many is the number 1? Say it loud, don't be shy. How many? 76. Why 6? The 0 at the end, the 0 and 0 is coming after whole number, and the decimal is present. Here's the decimal. This is the decimal. Oops. Why is taking this? The decimal is here. Here's the decimal. Can you see it? Don't worry about this comma. This has nothing to do with the sig figs. The comma is just for us to know is this value hundreds or thousands, whatever, correct, or millions. So how about number 2? So this is 6. Number 2, how many? Come on, guys. How many? 2? Why 2? Do we have a decimal? So one of the conditions is not met, correct? So we are missing one of the conditions. You have to have them at the same time, you see. So this is what? 2, just 1 and 2, those 2. Okay, and the comma is not part of the decimal. Now, how about if I'm playing smart, I will add here just a decimal here. So if I add here a decimal here, now it's 2 years, correct? So I will add a decimal here. This is 2, correct? But I say it's 1, 2, 0, 0, 0, 1, 2, 0, correct? And then 0, 0, 0, and then I put decimal here. How many now we have? How many? I put the decimal here. No, not 2, guys. Those zeros are N0, but are they meeting the conditions? Yes or no? They are coming after whole exact number, and the decimal is present. So how many we have here? 6, correct. This one has 6. Okay, number 3. How many do we have? How many? Come on, guys. How much? You can't see it? I can push it up here a little bit. Hold on. And I can make it bigger here if you want. Okay, let me take the stuff here out. And you can tell me now. We said this one here came out to be 4, came out to be 6. This one here came out to be 2. How much number 3? You want it to be bigger than this? You can see it now, correct? Okay, so how much number 3? 7. Why? Because the end of zeros are what? Significant. They have the decimal, and they come after the number 7, whole exact number. So this is 7. Perfect. So how about number 4? How many? 5. So this is decorating. Those are locating. There is no exact number before them. So the only significant are the whole exact numbers, which is 5, correct? So how about number 5? 2 or 3? 2. Why is 2? A decimal is missing, correct? This is 2. How about number 6? 3? Are we sure that's 3, not 2? 3, why? The 0 here is significant or not? And why? It is what? Significant. Why is it significant? The decimal is present, and it comes before whole exact number, which is 3. Correct? So how many we have here? 3. Okay. Number 7. How many? That's easy, number 7. Those are called trapped 0. Trapped between 8, value of 8, exact whole number, and value 2. So this is how many? 4. How about 8? That's easy. The 0 is trapped between, because the exact number will take priority over the decimal. So this one is called trapped 0, between the 1 and between the 3. So we have this one, how many? 6. So how many number 9? 9, 4. Now we are professional here. That's 6. Okay. Number 10, 3. Number 11. How about 3? 3 or 6? 6. Why is 6 correct? The decimal is present. The decimal is present. And this end zeros comes after the 2. So this is 6. Correct? So how about the last one? We have 2 commas. Comma here and comma here. That will tell me that I have millions. Commas has nothing to do with the suffix. You can take them out. I put the comma just to facilitate for me the value, the amount of the value. This million, correct? That's 2,635,008. So how many suffixes we have? So 4, 5, 6, 7, 8. Why is 8? Why is the 0 is significant? Same thing. We have the decimal is present, the decimal is present, and the number 8 is present. So I think by far we did very well. So let's do now okay, now sometimes you will be forced to round. Look at the rounding out. Sometimes it's not in the slide, but sometimes in the online assignment, you'll be forced to round the answer to 3 suffix or whatever, 2 suffix. But come on in. Yes, come on in.